All right. In this video, we're going to be talking about undrained stress paths for sand. So we usually start with drained stress paths. It's a little more intuitive to think in terms of a drained stress path because we know the stress condition we're imposing on the soil. But a lot of the time, we have to worry about undrained stress paths. And, a lot of the time we think of sand as being drained and clay as being undrained. And, that's not really true. It's not an equivalence there. Sand can be drained or undrained, right? If we load it really fast relative to the rate at which water can dissipate, it can be undrained. Clay can be drained. It may take a long time for the water to drain, but eventually it may change volume. So it is important to know how to do both drained and undrained stress paths for both kinds of soil. So what undrained means is that the volumetric strain is zero during loading, right? It's not allowed to change volume. We can impose that in a laboratory test really easily, either by closing a drain tap on a triaxial compression test or by doing a constant height simple shear test. So in a laboratory setting, it's actually pretty easy to get undrained behavior. It can happen in the field, for example, during earthquakes. An earthquake happens quickly, sand doesn't have time to drain during an earthquake, and so it may behave in a way that's undrained during earthquake loading. Since volumetric strain is zero, the void ratio doesn't change, right? So E dot, which is dE dt, is zero. The void ratio just stays the same during the whole loading path. So let's look at what happens then if we have two soils, same initial effective stress, but different initial void ratios. So one thing you should notice, there are multiple ways that you can get to be loose of the critical state line, right? There's the critical state line. We talk about it as being loose or dense of critical, and certainly you could go above the line by becoming loose, you can go below the line by becoming dense, and that would be at a constant P prime value. What we'll look at later too is that technically you could be at the same void ratio and be dense if you're at a low effective stress, but then you increase the effective stress and you become loose of critical. So even though we call it loose or dense of critical state, it's not solely a function of density. It's a function of the combination of density and effective stress. So anyway, here we have the same P prime and the void ratios are different. This one is loose of critical state, and we're starting at this point and moving that way, right, until we reach the critical state line. So what we find is that P prime will decrease for the loose of critical soil, whereas the dense of critical starts here. Initially it's a little bit contractive and then it goes over to the critical state line. So P prime at failure is higher for dense sand than for loose sand. Therefore the dense sand is stronger than loose. Okay, and one thing that I'll point out here, I said that initially P prime will decrease and then it will increase for dense sand. And that's related to the dilation behavior for drain loading of dense sand. Okay, we talked about how dense sand initially is a little bit contractive and then it becomes dilated. So let me just make a little sketch right here. Okay, so here this would be void ratio versus, say, epsilon Q for a dense sand, and here's the initial void ratio, E naught, right? So we know that eventually this sand is going to dilate, but before it dilates, it's slightly contractive, and then it will go up, right? Well, there's no void ratio change anymore for undrained loading. So this is drained, dense of critical DOC. Okay, if we go to undrained, the void ratio can't change, but if the soil tries to contract, that gets manifested as an increase in pore pressure. The particles are trying to get closer together, but they can't do it because we're not letting water out. Therefore, more pressure goes on the water, and the pore pressure goes up. So there's a one-to-one correspondence then between the dilative behavior and the pore pressure behavior. So now if we look at pore pressure versus deviatoric shear strain, I'm going to call this U sub E, excess pore pressure, right? Now this is going to be, I'll label it down here, undrained dense of critical. Initially, the pore pressure goes up a little bit, and then it comes down, right? So if the soil is trying to contract, more pressure goes on the water. If it's trying to dilate, then the water is actually holding the particles together. It can't, the soil would swell if we let water in, but we're not letting any water in. So that makes there be a negative excess pore pressure. So anyway, that's why I was talking about this soil exhibiting dilative behavior, even though it can't technically dilate, right? We're not allowing the void ratio to change. All right, let's go down here now. This is the other scenario that I was talking about, where we have the same initial void ratio, but different P primes, right? So here's the consolidation stress for the one that's dense of critical. It's a fairly low consolidation stress. Here's the consolidation stress for the one that's loose of critical. And maybe an easy way to think about this is that if you put your knuckles together, if you push really hard against them and push your hands like that, maybe you could force them past each other without having them separate too much. In the extreme case, you might even break your knuckles. Definitely don't do that. If you barely push them together a little, then your hands can separate a lot more easily, right? So the sand will be more dilative when it's dense of critical, when it's consolidated at a low effective stress. So P prime at failure now is the same. Okay, notice that the one that's dense of critical, I should have drawn the little tail here. It initially builds up positive excess pore pressure and then reaches the critical state line. The one that's loose of critical just goes straight to the critical state line. Right, and let me label the CSL here. All right, so what we find is that P prime at failure is the same. And what that means is that the final strength is actually the same for these two soils, right? We'll see later that if you reach, in QP prime space, if you're on the critical state line and P prime is a constant number, then Q is the same number. And, the strength is going to be the same in both of these cases. Therefore, what we find is that the critical state undrained shear strength depends only on void ratio, right? If we know the initial void ratio, which is also the final void ratio, then we can calculate the stress at failure, or the strength. It does not depend on the initial consolidation condition. Kind of an interesting thing. All right, so let's talk about some principles for drawing undrained stress paths. There are a few things that you kind of have to remember when you draw these, but there aren't that many principles. So if you just memorize these, you'll be able to draw any stress path you want. First of all, make them internally consistent, right? You have Q versus P prime in the upper left, and then Q versus epsilon Q in the upper right. The Q's have to line up, right? It's the same Q that you're plotting, so those have to be internally consistent. Same thing for the E axes and the P prime axes. All right, so then the second thing, we know that change in void ratio is 0. So void ratio is going to stay the same. Therefore, you should draw the E versus P prime or E versus natural log of P prime stress path first. So sometimes we put the x-axis as natural log P prime, sometimes it's just P prime. In any case, draw the one that's E P prime first because we know what's happening there. That's a little different than what we did before, right? We drew Q versus P prime first for a drained stress path. Now that it's undrained, we'll do E versus P prime first. All right, here's one that you just kind of have to memorize. Soil that is dense of critical will mobilize a peak friction angle, right? So loose of critical won't. And I'll show you what I mean by that. That'll become clear in just a second, what I mean by peak friction angle. Okay, soil that is dense of critical will be initially contractive before becoming dilative. So that's that little part of the curve right there. Don't forget that part. It contracts a little bit, then it dilates, right? And finally, undrained stress paths are initially vertical in QP prime space. So even if you have a triaxial compression stress path that has like a 3-to-1 slope for drain loading, this undrained stress path is going to be vertical initially. All right, so let's take a look at what's happening in direct simple shear, undrained stress path. And we're going to start, I'm going to label these here. So the blue line will be, maybe I'll label it down here. Blue line is loose of critical. And then I'll have you draw the densive critical one too, and then I'll draw it in so that you can see what it looks like. But you should take a stab at it first. All right, so we're starting here. That's our initial void ratio and initial P prime. And then we know the stress path is horizontal and it's going to move straight to the critical state line. So it just goes straight from right to left, right? And it ends up right there on the critical state line. So we've drawn one of them. That one's pretty easy. All right, now what we need to do is figure out what the QP prime stress path looks like. So we draw these little dashed lines up here. There's our initial point. So I'm assuming this is like a simple shear test. We're starting on a K0 consolidation condition. So the initial vertical effective stress is bigger than the initial horizontal effective stress. And then here's the line up here. That's where we end up, right? So we have the beginning point and the ending point. And we also know that the stress path in QP prime space has to start out vertical. Those are the only constraints we have. We have an initial point, a final point, and we have to get from one point to the other. So the way I've drawn it is one possible path that satisfies all those conditions. There are other possible paths. It could start here and not really mobilize a peak. It could make a bigger peak and then come down. All of those would be okay. Different soils exhibit those different paths. Just depends on the characteristics. All right, never mind this red line for now. I'll come back to what that means in just a second. Okay, so now we're going to go over to the right and do Q versus epsilon Q. So we're starting at a K0 consolidated value of Q. Then we're going to end up here. And along the way, we're going to come to a peak in the stress strain curve right there, right? So those are the conditions that we have to satisfy to make this internally consistent. So here's the stress path. It comes up to a peak in stress strain behavior and then comes down to critical state. All right, now we have this other easy one, void ratio versus epsilon Q. And of course, void ratio is constant, so it's just a horizontal line. All right, now this void ratio versus epsilon Q is not really very meaningful. Sometimes we might look at that just to make sure that it was undrained. Like if we measure some volume change and the void ratio changes, then we didn't really achieve our objective of having an undrained test. But this is actually not interesting to look at, E versus epsilon Q. So what we do instead is plot excess pore pressure versus epsilon Q, which is what I'm drawn down here on these axes. So here's 0 excess pore pressure. And then this soil is contractive the whole time. So you can see here, right? It starts out vertical and then P prime is decreasing as we go. And the way that we'll figure out how much excess pore pressure there is to look at what the stress path would be if there was no excess pore pressure. No excess pore pressure means drained, right? If we're doing a drain test, there's no excess pore pressure. So we know what that stress path is. That's the red line right here, right? So that red line would be a drained direct simple shear stress path. And we can then compute what the excess pore pressure is because it's just the difference, right? So here's the drained stress path, no excess pore pressure. Here's the actual stress path that we've measured that has some excess pore pressure. And the difference between them is UE. So the excess pore pressure is just P prime drained minus P prime undrained, where P prime drained is kind of a fictitious quantity, right? We didn't actually do a drain test. We just know that that would be the stress path if we did it drained, so we can calculate excess pore pressure. So in this case, it just goes up, reaches a plateau, and we're good. All right, so what we're going to do next is sketch an undrained stress path for the sand that's dense of critical state. Let me switch markers. So let's have it start. Let me think about this. I'm going to have it start here at the same void ratio, but a lower P prime value, right? So I've drawn the initial point, and your job now is to pause the video and get a piece of paper or use your tablet or whatever you have. Try and make a sketch of what that dense of critical undrained stress path will look like, and then come back and we'll go through it together. All right, great. Welcome back. And let me go through and draw this undrained dense of critical stress path. So initially it's contractive. So we're going to come down, P prime decreases, and then it goes back to the right and dilates and reaches critical state at the same point as the elusive critical one, because we started at the same void ratio. So now, and by the way, I'm plotting the x-axis here as p prime instead of ln of p prime. I'll talk about this in another lecture where we talk about differences between sand and clay. But basically, the critical state line is curved this way. If it's p prime, you know, it curves to where it's curved down like that. If this was the natural log of p prime and we were looking at sand, the critical state line would curve the other way. And anyway, we don't have to get into it here, but just a little preview for what's coming later. So I'll go back to my green pen and we can come up here. The nice thing about using p prime instead of natural log p prime is that everything should line up vertically here, right? Because if we do p prime on the top, we never do q versus ln p prime, just q versus p prime. And then we do e versus ln p prime. We have a natural log on the bottom and just a p prime on the top. Makes it a little bit confusing. All right, now we know that we're going to start at this point and we're going to end at this point on the critical state line. And we mentioned before, soil that is dense of critical will mobilize a peak friction angle. That's number 3 that we had to memorize up here. Well, what I've done is drawn in the line representing the peak friction angles right there. Okay, now we don't know exactly how much it's going to mobilize, but this is basically a guess, right? We know the peak friction angle is going to be bigger than the critical state one, so I've drawn it in there. And what we can do now is draw a initially vertical stress path, and it has to come down to this point, right? It's going to be initially contractive, so it goes over here, and then it's going to reach this peak friction angle line and then come down there. So here, let me zoom in. I'm going to undo a few of those lines. It's really messy. All right. Whoops. Let's undo one. Okay, so we're starting vertical here. We're going to go up that way and then reach failure right there. Okay, now it may be a little bit confusing to think about mobilizing a peak friction angle in this case, because we did not mobilize a peak in the stress strain curve. So let's come over here, and we're starting now at a lower Q just because we're at a lower initial P prime. And then our stress strain curve will end up here at the same point as the other one, like this. And it seems strange that this one mobilized a peak friction angle because it doesn't have a peak in the stress strain behavior. For drain loading, we did have a peak in the stress strain behavior, and that's when we mobilized the peak friction angle. Here we mobilize the peak friction angle just when the line crosses over the critical state line. You can see now we're tangent, at this point, we're tangent to the peak friction angle line. So that's where we mobilize the peak friction angle. It's at a lower stress ratio. So anyway, that's our stress path. And then, of course, E versus epsilon Q looks the same because, you know, we're keeping the same void ratio the whole time. And then if we plotted the excess pore pressure versus epsilon Q, initially contractive, then becomes dilative and goes down like that. So there's our final line, and we've got our full stress paths for this one. Okay, let's do the same thing for triaxial compression. Okay, the only difference now is that that red line is the drained stress path for triaxial compression stress test, and it's at a 3-to-1 angle instead of vertical, right? For direct simple shear, it's vertical. So anyway, we're still going to start elusive critical. We go straight this way, end at the very end. The process is actually kind of the same as for a direct simple shear stress path. Then we start here. This one's isotropically consolidated now, right? So that's another difference between triaxial compression and simple shear. A lot of the time we start at Q equals 0 for triaxial compression. So we're going initially vertical and then reaching a peak and curling back down and around to the critical state line. And so here's our stress strain curve. Okay, and then I didn't even take the time to draw void ratio versus epsilon Q because it's not interesting. So let's just draw excess pore pressure versus epsilon Q. Excess pore pressure does vary, so that one is more interesting. All right, and once again, let's start here with the point at the same void ratio, but at a different P prime to make it denser critical. Actually, let's vary it up a little bit here. Let's start it at a lower void ratio. Let's start it right there, just so that it's not exactly the same as the previous one. We're adding a little bit of a challenge here to draw this stress path differently. Okay, so again, there's the initial point, and you should be able to draw the rest of the stress path. So go ahead and push pause, give it a try, come back in a minute. All right, so we're starting at this point, and we're going to draw the undrained stress path for triaxial compression test. So we know it has to be initially a little bit contractive, so it moves to the left, then it moves to the right, and we're ending right there at that point. Right, so here's the lines. This one goes that way first, and then reverses direction and goes back. Okay, so let's draw our points up here. There's our starting point. We're starting isotropically consolidated. Now we're going to end on the critical state line a little higher up than the other test did. So this one's going to be a little bit stronger, right? It makes sense. It starts at a lower void ratio. It's denser. It should be stronger. So, and we're going to come out to this point right there before reaching a peak friction angle and ending up here. So this stress path is going to go something like this, reach the peak friction angle, and then fail along that path right there. Okay, and we come down here. It's going to end at this point. Okay, so the initial stiffness. This is a tricky one, right? The blue line is a little less dense, but it's starting at a higher vertical effective stress, whereas the green one is denser, void ratio is lower, but it's starting at a lower effective stress. Okay, so we don't know if the initial stiffness is going to be more or less than the blue one. So I'm going to draw it kind of just like similar, maybe something like this, and then it will fail like that, reach critical state up there. Okay, so note that the green line, it's consistent, internally consistent with this stress path. That's the thing that really matters. Then for excess pore pressure, we're going to start up here, come down, and become dilative, right? So it basically looks very similar to the direct simple shear stress path. The only thing is that if we're computing pore pressure now, it's going to be the difference between this point and that point. Instead of a vertical line, right, it's going to be that distance. So if we did the test without any excess pore pressure, it would be the red line, but we have to compare with that to get the excess pore pressure. Okay, and that's it for undrained stress paths for sand.